Today, I'm excited to have Dr. Jeff Zweerink, the UCLA grad with his specialty in astrophysics and also one of the senior scientists at Reasons to Believe. Welcome to the show, Jeff.
Don, it's good to be here today. Looking forward to our conversation.
Yes, I noticed in the past whenever we're together, people assume we're twins, but actually that's not true at all.
I was trying to wear the same shirt, So.
Yeah, the 5'7" guy, and what are you, 6'5"?
I'm 6'4", yeah.
6'4", yeah, and the 5'7" bald guy. People often confuse us. So in general, many Christians shy away from science because they assume that it's in conflict with their faith, or there's a whole conflict model that people these days frequently bring up. So you're different in the sense that you went deeply into science. So the question is, how did you get started in science?
Well, so it's interesting that you mentioned that, because I have encountered that in talking with people in the church, that they perceive science to be a threat to Christianity, and people in science perceive the church to be a threat to science. And so, I've kind of lived in that middle ground where, no, really, science and Christianity work together. And one of my first memories, I was probably 3 years old, no more than. And my dad was in the basement, and he was giving a chemistry demonstration to a group that my older brother was involved in. And, it's the kind of thing where you dip a ball in liquid nitrogen and throw it on the wall, and it shatters, and you mix certain chemicals together, and they make cool shapes or weird noises or funny sounds. Just being fascinated by all the different things he could do. And I've seen that demonstration a lot, but one of the points he makes out of that is that, this all looks like magic, but the reality of it is we understand how all this works. And so my dad is a PhD chemist, was a professor for quite a number of years. And I've just been fascinated in science for as long as I can remember. But one of the other early memories I had was actually my parents being baptized in the 102 River outside St. Joe. And again, I was about 4 years old. And so so my interest in science dates back as far as I can remember, but my foray into Christianity, if you will, and understanding what Christianity is about, that's also, for as long as I can remember in my life, these two things have been a part of what's going on.
So kind of the wonder and the awe you got from studying science, and the wonder and awe you get from realizing that God superintends all this, and that there's a purpose and mind behind it, really motivated you to pursue science.
It really does. I mean, if it comes right down to it, I love knowing why things work the way they do. And so, if I give a brief explanation of what scientists do, is they figure out why things work the way they do. And, that's what a biologist does. That's what a chemist, all of the different sciences do that. And so I went into physics because that's kind of how the world works. And that's what particularly fascinated me. But I love figuring out why things work the way they do.
So how do you go even further specialized? How do you go from, I want to know how things work, therefore physics, and then to astrophysics? How do you get that narrowing of focus?
Yeah, that's a good question. So, my dad was a chemist, and I enjoyed what he did. And so as I was going through high school, I was going to be going to chemistry. My senior year of high school, I took a physics class. And as much as I loved chemistry, I loved physics. It was like, oh, wow, this just made sense.
Yeah.
The mathematics by which you could calculate things, the simple principles by how well things work. And so I went into, when I went to college at Iowa State University, I went in as a physics major. I eventually switched over to a astrophysics side of it when I got to actually, it was related to an event that happened my sophomore year of college. Is that Hugh Ross, who is the president and founder of Reasons to Believe, came and spoke at Iowa State, and I heard him, and I was kind of in the midst of growing in my Christian walk, wanting to know what God might have for me, and I realized, hey, here's this possibility of being both a Christian and a scientist professionally, and I thought, hey, that was pretty cool. And so it got me thinking, what area of science does Christianity and science most overlap? And it seemed to be that was more in the astronomy astrophysics realm. So I picked up an an astronomy minor, and then when I went into graduate school, I went into astrophysics.
So I guess for many people watching this show, they've heard terms like astrophysics, but they don't really understand what is the difference between physics and astrophysics.
So the way I describe it is physics is figuring out how things in the world work. Astrophysics is doing that with a telescope. So, there's lots of different areas of physics. There's high energy physics, there's low energy, there's condensed matter, but there's a whole slew of different ranges of physics. Astrophysics is just trying to take those same principles and apply them to what's going on out in space.
So Galileo's
I am far more physicist than I am astronomer, if you will.
So you're saying Galileo's insights still apply, that the heavens work the same way. Physics is the same there, but with different ingredients, one might say.
Exactly. In fact, if Newton and Galileo weren't correct that what happens here is the same thing that happens out there, there would be no astrophysics that's actually a scientific discipline, because the way we figure out what's going on there is we measure the laws here, and then we go out and say, that'll explain that phenomenon.
So spectroscopy works the same both places?
Exactly. Yes. In fact, I forget when it was, but the first place we discovered helium was actually on the sun. We can't go to the sun and do the experiment, but we found lines for this element that we didn't find anywhere on Earth, and we realized, this is helium. And so yes, spectroscopy works the same out in the cosmos as it does here on Earth.
That's excellent. So we're talking a little bit about the universe and about studying the universe and the elements within the universe. So I guess the next question is, in general terms, could you tell us how the majority of cosmologists say this universe began?
Well, I would say that the reigning paradigm, or the dominant model of how our universe works, is an inflationary Big Bang model. And so that has this idea that the universe is expanding. It's expanding from a very hot, dense initial state. It's cooling down as it does. Laws of physics are the same throughout the universe. The amount of usable energy is decaying over time. And so these are fundamental features of our universe that interestingly match with how the Bible describes the cosmos, if you will. And then the implications of there being this Big Bang is that there's a beginning, or a marker, or something that marks the beginning of our universe. Now, I will say that if you go out and ask 10 different scientists, you're probably going to get 10 different answers about what that Big Bang is, or whether there's a beginning, or is it genuinely beginning, or is it lack of, you're going to get lots of different answers about how that, but there really is a lot of evidence that points to, there's at least how we see our universe, there's some that had a beginning point to it.
Okay, so you have written two books that I know of. One's more of a booklet, Who's Afraid of the Multiverse, and then the longer, newer book, Escaping the Beginning. What was your motivation for writing those?
Well, if you'll notice, there's actually a third one I've written called Is There Life Out There?
Oh, that's right. I read that one.
Every one of those is questions. And so in my work at Reasons to Believe, as I've developed apologetic arguments and thinking about issues, every one of those are questions where it's like, oh no, there can't be a multiverse. That's not scientific. And then I realized, oh, wait a second, there's actually scientific motivation for there being a multiverse. So who's afraid of the multiverse? What's going on in here? And so these are questions that I've had about things related to science and Christianity, where I've had a chance to kind of dig in deep and say, all right, what does the science have to say? What does Christianity have to say? And are they in conflict? Do they work together or not? And so, who's afraid of the multiverse? Is there life out there? And can we escape the beginning? Those are kind of the questions I've had, where they're legitimate questions that they could go either way. And so I'm just wrestling with, as a Christian, is this going to be something that's going to show Christianity wrong? The short answer is no, but that's basically what I'm doing.
One thing I appreciate about your books is many times I read books on apologetics or on other topics, and the scientists present views as if this is the correct view. Whereas in all your works that I've read, you bring in a variety of viewpoints and give the relative strengths and weaknesses, and admit that there are motivations beyond simple rejection of God for different ideas that show up among the scientists. like the motivation for Multiverse, it goes beyond simply we don't want a beginning, or we don't want a designer for this universe, so therefore we'll add a bunch of universes. It's refreshing to see someone acknowledge that there are other viewpoints.
Mm-hmm. Well, and that's really kind of motivated by the way I think about things. It's like I would far rather have an accurate assessment of the situation so that I can make a good decision on what to do and what's right and the right way to think about it. And so my hope in writing those books is that you come away saying, okay, not that I have all the answers, but at least I have an accurate picture of what the landscape looks like.
Mm. So back to the origin of the universe, what evidence do we have in general terms that the universe began?
So I would say probably the strongest piece of evidence, and it's actually kind of a line of evidence, not so much a single piece, is as people have looked at trying to understand the history of the universe, where we realize the universe is expanding. And so you ask that question, how far back can you push that? Do you end up at a beginning? The evidence seems to keep pushing towards a beginning. So when Einstein first proposed a general theory of relativity, that indicated that the universe was expanding. People said, no, it need not be expanding. It could just be static forever. And then we come and find out that, lo and behold, we measure Hubble and others measure the expansion of the universe and say, no, that's not good. So if it's expanding, does it have a beginning? Well, it could be oscillating, and yeah, it could have a beginning, but not really a beginning. Or it could be a steady state model where it's expanding and new stuff coming in. Or it could be expanding in a way that it doesn't have a beginning. And so all of these options were being thrown out and wrestled with. And what ended up occurring was that all of these different options some piece of scientific data said, no, they didn't work. And so in the late 1960s, early 1970s, people were saying, all right, if the universe is expanding and general relativity is true, and energy behaves a certain way, there are kind of 3 or 4 conditions that seem to be very reasonable, then you can point back and say there's a boundary to time or to the universe. So as you run backwards in time, you eventually run into this singularity. And in this particular instance, it's where the laws of physics broke down, and that's the beginning of the universe. And so there are these singularity theorems that, starting in the 60s and 70s, seem to indicate that no matter how you slice it, as you run backwards in time, you eventually run into this boundary where our universe begins to exist in some fashion. And so I would say that's the strongest piece of evidence.
Well, I just thinking back to the news stories over the last 20 years on the origin, and how you see stories about the Big Bang Theory is dead. And then you read the article and you see that one of the competing models has been eliminated. And then you see the Wilkinson microwave anisotropy probe went up, and they said the universe has the constituency of this much dark energy, this much dark matter, this much baryonic matter, and it says in the geometry is basically flat.
Mm-hmm.
What does it mean when you say the geometry is flat? Isn't it anywhere you look? I don't. What does flatness mean with geometry in the universe?
That's a great question, and it's one of those that I finally understood this weird comment that was always made back in geometry when I was in the geometry class I took in high school. So we tend to think of flat as in our 3-dimensional universe, like the surface of my computer screen is flat. It's related to the shape, but it's almost always kind of this 2-dimensional thought to it. It's like there's no 3-dimensional structure, and it's just different than the way they're thinking about. So you could imagine 3 different scenarios, and let's go down to 2 dimensions because that's what we can think about. You can imagine a surface that is flat. So, that no matter how far it goes, it just kind of continues going in that same direction, and there's no real structure to it. You could also have a surface that is curved. So imagine you look at your world atlas, and it's flat on the piece of paper, but you could also take that and wrap it around on itself. That's a curved geometry that is curved in a closed fashion, that it comes back on itself. Or you could have a saddle, which is where it just kind of goes it's not flat. It gets further apart, and the way to distinguish all those. So there's the open, which is the saddle. There's the flat, which is the piece of paper, and then there's the closed, which is the sphere. What distinguishes all of those is how parallel lines behave. So in a flat geometry, and this is the comment that was always made when you were talking about parallel lines, is that parallel lines stay the same distance apart. They remain parallel because as you draw two parallel lines on a flat sheet of paper, they stay the same distance apart. But if you go to a closed geometry, those parallel lines now converge. And you can think about that like a globe. If you go down to the equator, all the lines of longitude, are parallel to one another at the equator. But as you move away from the equator, those lines converge. And in a saddle, the parallel lines diverge. And so it's this kind of more technical mathematical definition that people are talking about. It's what happens to parallel lines. So in a flat geometry, parallel lines stay parallel. In a closed geometry, parallel lines will converge. In an open geometry, parallel lines will diverge. And that distinction has implications for the way what we will measure when we go out and look at the cosmos.
So the Euclidean geometry I learned in high school, does that apply to our universe?
The Euclidean geometry is a flat geometry.
Yeah.
Now, to our best measurements, our universe looks flat. The challenge to that is that a flat geometry, so let's say flat has a measure of 1 in the parameter we're using. Flat is 1, closed is, or let's call it 0, just because that makes it easier. Flat is 0, closed is negative, and open is positive. So in any sort of measurement I'm going to make it 0 plus or minus some error bars. So we measure it to be flat, but the error bars include both open and closed. So at least to 2 or 3 places of the decimal, the geometry of our universe looks flat, but there's still a little bit of ambiguity or not definitiveness about whether it's flat or open or closed. All 3 of those options are still in play given the way what you're trying to measure there.
So if it's slightly open or slightly closed, what does that say for the past or future of the universe? How would that change the projections?
Well, so if it's slightly closed, then this actually becomes a rather complicated question because there's lots of ways you could have a closed geometry. The simplest is just a sphere. So you take the surface of a ball. That's a closed geometry that is curved. It's a negatively curved closed geometry. But you could also have a donut. That's also a negatively curved closed geometry, but it's got a different, the technical term would be topology than a sphere would be. So now the question is, if it's closed, what's the actual topology of it? And that's going to be a very complicated, difficult question. But a closed geometry is going to have a finite extent to it. Whereas when you're talking about flat or open, those could, in principle, and in fact, the naturalist explanation or simplest, most straightforward explanation is that those could be infinite in size.
Infinite in the future or past?
Infinite in size.
Oh,
and
size, I see.
When you start talking about space-time, those terms are ambiguous there. And so it becomes a little bit more complicated question. And so we could spend a long time talking about infinities and do they exist and actual, and there's a whole fun discussion there, but those are kind of some of the implications.
Yeah, that's exactly where my mind went, was if it began, then you're starting with 1. How do you reach infinity when you start with a finite number, was my first thought when you said that. And
well, that's a great insight, because and the way that the scientists would answer it is saying it's not that the universe starts small and grows infinite, it's that it was infinite from the very beginning. Because that's the one thing that everybody seems to agree on, is that things are finite, cannot grow to become infinite. Things that are infinite cannot be subdivided into a finite set of finite quantities. That's the one thing everybody agrees on. But the open question is, and as a Christian I would ask it, did God create the universe infinite or finite? And we don't have a definitive answer to that from a scientific perspective.
And Thomas Aquinas thought it could be either.
Exactly, yes.
Okay, so we talked earlier briefly about the Wilkinson probe, and we said that the universe has dark matter. What is dark matter?
Well, this is one of those places where you see the ingenuity and creativity of scientists in naming things. That when we look out at stars, we see the light from the stars, and that's how we measure what's going on there. Really, the where we realized there was something like dark matter is when you're looking at how do galaxies behave, and it's a little more complicated than that. But that was the prevailing place where the research was being done. Is when you look at a galaxy, the way Newtonian dynamics and even Einsteinian dynamics work is that there's this very cool property that if you want to measure the mass of something inside an orbit, all you have to do is measure the orbit. So if you want to measure the mass of the Earth, look at the orbit of the moon. That will tell you how much mass the Earth has. It doesn't matter how massive the moon is. All it measures is how much mass the Earth has. And similar to if you want to measure the sun, look at the orbit of the Earth. So we can look at the orbits of stars in distant galaxies and figure out how much mass is in the galaxy. Well, you can also look at the galaxy and count the stars and figure out how much light is there, and from that figure out how much stars there are. And the amount of mass that the orbits needed to explain the orbits was more than the amount of matter that was giving off light. So we came up with this cool name, dark matter. It's matter that doesn't give off any light. And so we measure it in galaxies, but we also measure it in clusters of stars. We measure it in clusters of galaxies. We measure it at all, well, we see the gravitational effects of it at all scales. And so it's this mass that doesn't give off any light effectively.
Yeah, I think I've seen a photo probably from the Hubble of a globular cluster that was lensing, like the Einstein lens,
right,
the galaxy in the distance behind it, and it was warping it obviously and distorting it, but it was showing up on all four sides. And they said there was not enough stars within that cluster to bend space enough to make the light do that. So they were saying that was, and the same type thing you're talking about is evidence for dark matter.
Right.
So you've already talked about why do scientists think that dark matter exists? So the question is, what is it? What are some of the candidates? Is it big things, small things? Is it subatomic? Is it massive? What are the candidates for dark matter? And you don't have to give all of them if there's a whole long list, but what are the better candidates?
Well, so there are kind of two classes of candidates that are the most popular explanations, but there's far more than that. I mean, I think I gave a talk once, and there's at least 8 or 9 different options of what the dark matter could be. But the two prevailing models out there are that both of them are subatomic particles. One of them where they're very massive subatomic particles, so far larger than the mass of a proton, like something on the order of 1,000 times the mass of a proton. Something, no, sorry, I take that back. But it's something on the order of a mass of a proton or larger. So they're these massive particles.
Right.
Or they could be, and so those are called WIMPs, weakly interacting massive particles. And then there's these other particles which are called axions, which would be very lightweight. So if we're talking GeV type masses for the WIMPs, here we're down on few EV, so 1 billion times less massive. That's kind of so they're axions and WIMPs are the two types of.
So there'd be a lot more axions in this case to make up
yes.
the mass of the WIMPs to be a candidate. Okay, that's
right.
one category. What's the other category you're saying could be possible?
Well, so you got the weakly interacting massive particles. The WIMPs is one, and then these axions would be the other. So
okay.
And those are the two that are well motivated from our model of particle physics, or actually slight extensions to the models of particle physics of what we know. And so they're not, our physics doesn't demand they're there, but they are, as you extend our standard model of particle physics beyond just the standard model, these are options that come into play without a lot of weird stuff, just naturally extending it into things that we think are going to happen anyway.
So in the last 20 years or so, have they made progress in this search? I'll just, as a little backup, at the National Conference on Christian Apologetics 2 years ago, I was giving a talk on God's divine simplicity concept, and a guy came into the wrong room, and I asked he realized he was in the wrong room, and I said, what are you looking for? We talked for a few minutes. He's looking for a science talk, one of you guys. And he said, I said, what's your interest? And he said, I research dark matter. And I wanted to sit and I had to give a talk, but I wanted to sit and ask him questions about how things were going. So I've got you here today. You're my substitute. Well, how are things going in the search for dark matter? Is any leads panning out? Anything looking better?
Well, there are a lot of experiments out there looking for dark matter, and the challenge of finding dark matter is that whether you're talking about axions or WIMPs, these are things that are very difficult to detect. In fact, that's why they were undetected for so long, and why we only measure the gravitational influence, is that they don't interact via electromagnetic interactions, which is how we do all of our experiments at this point. So you know, the WIMPs that we're looking at, we're just floating in a sea of WIMPs. They can go right through the Earth and be unfazed by that. So the question is, how do you build a detector that could detect something like that? And so there are underground detectors where you're looking for a place where a WIMP will hit another nucleus and cause some sort of scattering. Or you can look at the hearts of galaxies where there's supposed to be a bunch of dark matter and hope that it annihilates with itself and gives off a signature. Or the experiment that I'm working on, where you're looking for where the dark matter will self-annihilate and it'll create other particles that you can detect that don't have any other background to them. So the short answer is there's a lot of work kind of narrowing down what are the regions of parameter space that are still open or possible given our current measurements, but there's no measurements out there that say, oh yeah, this is dark matter, anything more than the gravitational effect. So it's a place ripe for somebody to make a discovery that they'll likely get a Nobel Prize for.
Well, maybe the guys at GAPS will find it. So what is GAPS?
So GAPS stands for General Antiparticle Spectrometer. So we're an experiment looking for dark matter, and the particular mechanism by which we will find the dark matter is that these WIMPs generally, when you look at the properties they have predicted from our standard model or beyond standard model predictions, they're their own antiparticle, which means that if two dark matter particles collide, they'll annihilate into pure energy and then produce a bunch of stuff from that energy. And they have enough energy that they can produce a proton and a neutron, and those two could coalesce and form a deuteron, is what the particle is called. Now, we're looking for something a little more extreme than that, because we're looking for the antiparticle of that. So we get an antiproton and antineutron come together and make an antideuteron. And if this scenario works, we've got a detector that is sensitive to antideuterons of a certain energy, which is the energy that we would expect them to be produced, and that there really seems to be no cosmic background for it. So this is a detector. We're looking for antimatter, so you got to put it way up above the atmosphere, or else it'll just be destroyed in the atmosphere. And you fly it around, hopefully in Antarctica, for anywhere between 30 to 90 days. And if we find 4 or 5 of these events in that certain energy range, that would be a good sign that we found dark matter, and that would tell us that it's one of these WIMP type particles that's the dark matter. So that's the hope and what we're shooting to try and find. So
I'm guessing so far nothing to report.
Well, we're still building the detector. We were originally supposed to fly in December of 2021 down at the South Pole, but with all of what's gone on with COVID-19, that's delayed everything. So it'll probably get pushed back a year. But you know, so it'll fly. Let's say it'll fly in 2022. We'll have a year to analyze data and hopefully something at that point in time. You know, realistically, we'll probably find upper limits, but we're exploring a range of parameter space that hasn't been explored before. So it's it's a very real possibility that we could find the dark matter there, and that would be really exciting.
You know, back to the cosmology issue. When I was reading on the origin of the cosmogony, I guess technically, when I was reading on the origin of the universe, I read where I think it was Alan Guth came up with the idea of inflation to solve the horizon problem and other issues, which leads to other possibilities, multiverse, etc. Mm-hmm. What is inflation?
So inflation, I give a little bit of the scientific discoveries that motivates why inflation was proposed, is that when we were looking, or when I'm talking about past astronomers, were looking at the heavens, trying to figure out what's going on, what they realize is there's this background radiation that we measure in microwaves now, that it just pervades the cosmos. Day or night, whatever direction they looked, it was the same. And we now can make very detailed measurements of that and find that it's 2.725 Kelvin, which is very near absolute zero. It pervades the cosmos. Doesn't matter what direction you look, and it's uniform in every direction to about 1 part in 100,000. I will make one little caveat. The fact that we're moving in a certain direction actually produces a dipole moment, but that's due to our motion, not due to the inherent in the radiation. The radiation is inherently smooth to about 1 part in 100,000. And so as people, as they found this radiation that pervaded all of space, realized that there's this incredibly homogeneous nature and isotropic nature to the universe, that every direction and every way and every time the universe kind of looks the same. And so you've got an expanding cosmos. Big Bang cosmology says the universe starts from this hot, dense state and expands. Well, where that radiation would have been produced in standard Big Bang models, it wouldn't be homogeneous, or it wouldn't be the same temperature in that part of the sky compared to that part of the sky, because the light from that part of the sky has been traveling towards us for 14 billion years. The light from that part has been traveling towards us for 14 billion years, but they haven't had time to communicate and come to the same temperature. And as you go further and further back in time, that discrepancy actually gets larger. And so that was one of the things that people were trying to explain. Why is it that the temperature, or that everything is so homogeneous in the universe? There's also, our universe is flat, but in the 70s, 80s, 90s, as we were looking at this, flat is an unstable point in our geometry. As the universe continues to expand, it will tend to go to either closed or open. And kind of an analogy to that is, you can imagine a pin. You put a pin, you can balance it on its top, but that's an unstable point. And as it moves away from that, it actually wants to go further away from that even faster. So flat is an unstable equilibrium point like that. And so, they knew that. There's also some questions of why there were no magnetic monopoles. And it was actually somebody trying to solve that problem realized that the physics indicated that our universe might have expanded very rapidly in the earliest moments of the universe. And by rapidly means that over in just some fraction of a second, the universe grew by, about 10 to the 26th times. Just an enormous expansion. And so this very rapid expansion, or this era of very rapid expansion, is referred to as inflation. And it actually now explains why the different regions of space all have the same temperature. If for no other reason, it's because things that were able to connect now expanded faster than the speed of light. So now that's why they're out of contact, but they were in contact at some point. It's actually a little more complicated than that. Right. It explains why things are flat, because you can imagine now taking a ball, which is very curved, but if you blow it up very large, but you can still only see that much of it, it's going to look flat in that little region. It explains why there are no magnetic monopoles. And so this region of inflation solved these 3 or 4 problems that we had in standard Big Bang cosmology very eloquently.
Yeah, I'm looking for the empirical evidence side. I remember several years ago, the BICEP probe was making announcements, turned out to be not accurate. That when they said they determined that they discovered evidence, the smoking gun of cosmic inflation, in the sense that I guess they were using PDF files or something, and it made the light was polarized, the wrong bipolarization or something of this sort, and whatever. It didn't pan out. They were kind of hedging their bets on certain data they had that didn't prove out. Has that been reclaimed, or are demonstrated that they didn't make a mistake, or is there some other empirical evidence for cosmic inflation these days beyond the it fits the model kind of
No,
evidence?
you're exactly right. There's the inflation was in essence invented to solve these three problems, but there are other observable signatures of it. One of the observable signatures is that when you look at the cosmic microwave background radiation, particularly the fluctuations, inflation says that the power at the bulk of the power should occur at a certain multiple. And I'm not going to go into the description of all that, but we've seen these graphs where it kind of goes up and it's got these bumps afterwards. Inflation actually predicts that that first bump will be at a certain place. And when we found the structure in the cosmic microwave background and then measured the power, it lined up exactly where inflation would say it is. The fluctuations ought to have a certain kind of spectrum to them, not a the spectral index, instead of being 1, ought to be less than 1, and we measured it to be less than 1. So it would be easy to say, oh, inflation was just invented to solve these problems and we don't have any observational evidence for it. The reality of it is there's a number of things that inflation predicts, and all of those predictions have been matched. The challenge is that there are other ways to explain those predictions as well. And so it's not so much that there's actually a lot of experimental evidence that supports inflation, but there's not this piece of evidence that distinguishes inflation from all the other explanations. And so that's where, if they had found this particular signature of gravitational waves, which inflation should produce, then that would have been a smoking gun. There's really no other way to produce those. And so that's what BICEP was looking for. They found some evidence of that in the polarization, which you can see is already one step removed from the gravitational waves themselves. And the way I understand it, it's they were using data from a PowerPoint presentation, and so they didn't have all the details in there. It was a little bit off. There was a signature at the 5 sigma level, which is kind of the standard for publishing something. And when they got the more of the data, that signature went down below 5 sigma. To my understanding, the signature never went entirely away. It just was no longer large enough to say we've definitively claimed that. And what my suspicion is that they've got some sort of signature, but it's not statistically compelling enough, and it was a little bit at the wrong place. So I do think so that's all, everything I've said that's what the scientific literature says. My suspicion is that as we study and have the sensitivity to actually find the gravitational waves, we're probably going to. But there are a number of people, a small number of people in the scientific community, but nonetheless a legitimate number, who are saying maybe inflation is just wrong and we need to be looking somewhere else. So it's entirely possible that inflation isn't correct, but there's a lot of evidence that points to it at this point in time.
So the LIGO isn't going to find the missing gravitational waves?
Well, LIGO is looking for a different region of the spectrum for gravitational waves than what the inflation would produce. You're going to need something like a space-based laser interferometer to be able to measure the gravitational waves that were produced during inflation.
Yeah, I can see somebody proposing that to Congress right now, funding that.
Well, there's been one out there where they're doing a lot of research on it, and this is something where you put 3 satellites that are 1 million miles apart, you shine laser beams between them, calibrate them to fractions of an inch, and can measure the gravitational waves. So that's an idea that's been out there for probably 20 years. I don't know what the time frame is, whether it'll get built. It'll obviously be an international project because it's a pretty large scale project, but people have been thinking about and working towards a project like that for quite some time now.
Okay, well, good luck to them. Dark energy. We talked about the Wilkinson Microwave Anisotropy Probe, WMAP. It said that is it the mass density of the universe, or that we're talking about, or the what the universe is made of, and it's like 24% dark matter, 70-something% dark energy, and 4% normal matter.
Right.
What is dark energy? Yeah.
So the way I remember it, and the numbers fluctuate, so I just kind of remember the general ones. is that all of the electrons, protons, neutrons, everything that we interact with, that's the normal matter. That makes up about 4%.
Right.
The dark matter is about 6 times that. So if that's 4, that's 24% of our universe is dark matter. That's probably some particle that we just haven't detected yet. And then the remaining 70 some odd percent is dark energy. Now, where we have at least some candidates of what the dark matter could be, the dark energy, we really don't have any good, I mean, we've got some ideas of what it might be, but there's really no good candidates out there. But what this is, again, it's something that we're looking at our observations and we ask what will explain these observations. The the impetus for thinking there's this stuff called dark energy is that as we're looking at mapping the expansion history of the universe, we can look at Cepheid variables relatively close, you know, within maybe half or 100 or 500 million to 1 billion light years away, maybe a little further than that because they get too dim. We can map out how far away they are, how fast they're moving away from us, and that gives us a measure of the expansion history over that period of time. And as we go further and further out, we can map out the expansion history of the universe. As we look at supernova, which we can see a large fraction of the way across the universe, what we see is that the measured expansion history shows that about 5 billion years ago, the expansion rate started accelerating. And so the most natural way to get that acceleration is some form of dark energy. And so when we now couple that in with looking at the cosmic microwave background and model everything and say, what's the best model? We see evidence for the dark energy in the cosmic microwave background radiation. We find it in the expansion history. We find evidence for it in the clustering of large-scale clustering of galaxies, these baryon acoustic oscillations. So there's lots of pieces of evidence pointing towards the existence of this dark energy. We just really don't know what it is and don't have any really good candidates for it at this point.
Dark matter doesn't interact with light, obviously, hence dark.
Right.
How is that different from dark energy? You're using the word dark on both of them. Is this energy that doesn't interact with light? Why the word dark?
I think more because it's like, okay, well, we didn't know what dark, you know, we saw this matter that was dark, so we called it dark matter, and we see this other stuff that behaves like a certain kind of energy. We'll just call it dark energy. I mean, I'm not entirely sure of the genesis of the name,
yeah,
but that's probably what it was. And really what it's saying is there's this component to the universe that we really just don't understand. We see evidence for it existing. We see that the practically speaking, the way it works is that it causes space that as space expands, it wants to expand even faster. That's kind of the general principle of it. What I suspect is going to be true of dark energy, if you will, is that it's actually a property of the fabric of space-time. So, you know, we tend to think of space-time as having dimensionality, that there's a length, width, height, you know, there's kind of, and that's all there is. Well, with the discovery of the Higgs boson, there are these scalar fields. And so that's actually just a property of space. There's the Higgs field. And so probably dark energy is going to be something like that. It's just a property of the fabric of space. And the way it shows itself is that as space grows large, it actually wants to grow larger even faster.
Okay, so it sounds like what you're saying is with the dark energy, it's a repulsive force, kind of like the opposite of gravity, but it's at such great distances. How would that even operate?
That's a good question, and what we can measure is how it operates, and the measurement of it is how it affects the space-time fabric of the universe. But there's a question of, you know, is it as a repulsive force? Is it a property of space-time? You know, these are the questions that scientists are wrestling with, and it's a mysterious enough quantity, if you will, that there's not a lot of really good ideas. You know, if you talk about it in terms of a particle, it becomes very difficult to explain, because if it's a particle, it should be enormous mass given where it can come into our standard model of particle physics and explain what it is. but we measure what we measure in terms of an effective mass is about 120 orders of magnitude smaller than that. And so it's a very difficult thing to wrap our minds around and get a hold of and understand. And so, you know, I'd love to say, oh, you know, like with dark matter, I can say, oh, here are some ideas. Here's what we know. There's a lot of details. There just isn't that with the dark energy.
So they haven't found an anti-graviton yet?
Not that I'm aware of.
Or
They haven't found a
graviton for that
graviton,
matter.
so we can't find the anti-graviton.
Yeah.